So in the last lecture, we talked about the necessary conditions that realizes circular polarized response. In today's lecture, we will start with various techniques that realizes circular polarization in microstrip antenna. Now the first technique which we are going to consider are a single feed configuration and a dual feed configuration. Here I am taking the example of the rectangular patch. Now whatever discussion which I am making here with respect to the rectangular patch on the similar lines, okay, with slight modifications subject to the geometry what we are considering, all those explanations or concepts are valid for circular microstrip antenna also and as well as equilateral triangle. Of course, I will talk about their designs also, how CP is realized in those other shapes. To start with, we will first understand how a single feed design and a dual feed design of this rectangular microstrip antenna yields a CP response. Consider this configuration. I have taken a nearly square patch. Okay, nearly square patch means L is approximately equal to W. To be precise, L by W can be in the range of 1 to 1.1. Okay, L by W can be in the range of 1 to 1.1. So I have taken a nearly square patch. What is required in circular polarization is I should excite orthogonal modes so that EX and EY component will be realized. What it means that I should be having a excitation of X directed current, that is JX, which will lead to EX field predominantly, and then I should have a Y directed current which will lead to EY, that is Y directed component field predominantly, okay, with respect to their principal plane of radiation. Now to achieve this, I need to excite orthogonal modes in the patch. Now what are the orthogonal modes in the patch is TM10 and TM01. These are the two orthogonal modes which are there in the patch. In earlier case, we have seen that if you put your feed point either along the width or along the length, in either of the two cases, you will excite only one of these two modes. That will give me linear polarized response. I want circular polarized response, so I should excite both the modes, right? So here I am choosing the field locations such that it will excite both the modes. Okay, just to compare that with respect to linear polarized. In linear polarized antenna, either I will excite it over here, which will excite 1-0 mode, or I will excite it over here, which will excite 0-1 mode. Okay, just for the clarification purpose. Now here what I have done, I have used a power divider circuit. This is my power divider circuit, or basically a microstrip line network. Okay, this is exciting my 0-1 resonant mode, and this is exciting my 1-0 resonant mode. The dimensions, width of these microstrip line is decided depending upon what is the edge impedance here. Okay, what is the edge impedance? This is depending upon that the width of this microstrip line is decided. Further, the difference of the individual line section should be such that it should excite orthogonal phase component, because see, apart from EX is equal to EY, or rather JX is equal to JY, what you require is phi x is, or phi x minus phi y mod should be equal to pi by 2 radians. To achieve that, what is done is the power divider network or the length of the power divider network is selected such that, for example, if this length from the coaxial feed to the edge of the microstrip antenna, if it is L1, then this length should be L1 plus lambda by 4, because lambda by 4 travel will give me pi by 2 radians phase shift, right? So this will ensure that the signal coming from here to here, remember both the signals are undergoing length L1 phase shift, but this signal will undergo additional 90-degree phase shift. So effectively at this point I am exciting say A amplitude 0. I am neglecting the phase introduced by L1, and I am introducing the signal as A angle 90, because effective difference in the phase is 90. So by exciting orthogonal modes, I have ensured that Ex and Ey are excited, okay, and then by ensuring the power divider network such that appropriate phase difference is added by ensuring lambda by 4 length, that ensures 90-degree phase difference between the Ex and Ey. Now very important component is, are we ensuring this equation, that is Ex is equal to Ey? The answer is partly yes. The reason is two resonance frequencies. Remember, L1 is approximately equal to LW, right? So we are merely using a square pattern. So if you really plot the resonance plot, okay, so if you plot the resonance plot, the two frequencies will be closely spaced, right? So in this region you will get Ex is approximately equal to Ey. Ex is approximately equal to Ey. So all these three conditions are being satisfied at the resonance of in the rectangular microstrip antenna to ensure circular polarized radiation. Okay, so these three conditions, this circuit, this antenna design along with the power divider circuit will give me a circular polarized radiation. Now instead of that, a dual feed design is there. In that, what we do, we are not using external or power divider circuit which is integrated with my antenna. Remember, this power divider circuit is integrated with my antenna. Now what is the disadvantage here? Apart from dual feed design, because see, dual feed design effectively is there in both the cases. Okay, although we are having a single feed, these two acts like a dual feed connections. So effectively dual feed design is there in both the cases. But here what is the problem is, you are integrating your power divider circuit on the same substrate which is optimized for antenna. So recall the disadvantage of microstrip line feed network for rectangular microstrip antenna or in general microstrip antenna. What is the disadvantage? You should have very small dielectric constant for the radiating patch and a very large dielectric constant for the microstrip line. In this case, you are ensuring same dielectric constant for the strip line which is being utilized for antenna. So your strip line will also start radiating. That will degrade your radiation feed or CP feed, circular polarized feed. So this is one of the disadvantage of this single feed power divider network configuration, that it will degrade the radiation efficiency as well as CP radiation quality. Okay. Now what is done in this case? Generally, what is done is you use a separate layer to connect or to generate the two 90-degree opposite fields. Means what? This is your layer where the radiating patch is present. Okay, and then on this layer you create a power divider network. Okay, so the substrate at the bottom can be chosen such that it is optimized for power divider circuit, and then these two connections will be brought to the patch through the shorting wires. So in generally we use this kind of a feed network to ensure that this effective radiation problem from the microstrip line is minimized. So over here the feed network is lying below the patch. Okay, feed network is lying below the patch, so that is the radiation from that is not getting affected with the main patch. Plus the dielectric parameters for this are being optimized for the microstrip line power divider network as against this, where you have both the same dielectric constant for the antenna as well as the power divider circuit. So in this case, that optimization of the properties of the microstrip line against antenna in terms of dielectric constant is done, and you do get a dual feed design that will effectively excite 0-1 mode and 1-0 mode to realize a CP radiation. Rest everything remains the same. Means what? How Ex is equal to Ey, their resonances are close, so Ex is approximately equal to Ey. Since orthogonal modes are there, you have a spatial phase difference of Ex and Ey plus phase difference is also maintained to be pi by 2 because you are ensuring that through the power divider method. Now the next very important question arises is over what band of frequencies all these three conditions are realized. Okay, because see, ultimately it is very difficult to realize all three conditions at the same point or over a band of frequencies, right? So there, from that perspective, we define a term which is already known to you, especially in case of circular polarized designs, a axial ratio bandwidth, axial ratio or AR bandwidth. Okay, because see, it is very difficult to realize Ex is equal to Ey for a wide band of frequencies. At the same time, getting this phase conditions along with that is also difficult to realize. So, what will happen if the deviation occurs between Ex and Ey or phi phase difference? Then the conditions for circular polarization is not properly realized. What will happen? That copolar component and cross polar component will be slightly different in the broadside direction. Then you will not have a perfect circular polarized radiation. To avoid that, to ensure that these three conditions are realized, because see, whenever a deviation from these conditions will happen, you are basically going towards the elliptical polarization. In circular polarization, co-polarization and cross polarizations are equal and these three conditions are met. But if there is a deviation from these conditions, definitely it is not a pure CP radiation. So a term is defined that a axial ratio less than 3 dB, that means the ratio of Ex and Ey, if it can vary, how much? Within 3 dB range. Okay, it's a logarithmic scale, so within 3 dB range it can vary. So that is the range of frequencies over which we define antenna is considered to be circular polarized. Again I am repeating, these conditions for CP may not be realized over a band of frequency. So that condition may be realized at a given point, say. That condition may be realized at a given point. Away from these two conditions, then what will happen? Your conditions for CP radiation is not met. Hence, we define a term called as axial ratio. That means away from these conditions, as the conditions are not met, but within certain range, the axial ratio is maintained so that co and cross polarization levels are nearly equal and the circular polarized condition is obtained. It is basically a 3 dB difference, means an elliptical polarization. But we assume that it is within our limit for a circular polarized radiation. So that is the way you define the axial ratio bandwidth. In best good CP antennas, in fact, we consider that limit to be less than 1.5 dB. Okay, but generally we do accept a CP condition where although these conditions are not met, but axial ratio remains within 3 dB. Okay, so here we talked about your single feed configuration using a power divider network. We talked about dual feed configuration using a power divider which is placed below and the pack is on top, in stack condition. Then we talked about advantage of this against this. Okay, so you can compare these two configurations against each other in terms of radiation efficiency and ease of fabrication also.